Today we are going into the investigation of photoelectric effect. Present before us is the diagram of a gold leaf electroscope and a zinc plate placed on top, and the zinc plate is negatively charged. Therefore, the gold leaf electroscope is also negatively charged. That's why you see the gold leaf actually diverge away from the vertical line. So what we assume is in the beginning we have a lot of negative charges because the whole thing is negatively charged. So what do we do first is we shine red light on it. We see whether the gold leaf will fall down or not. Or perhaps I use UV light, shine on it, and I want to see whether it will go down or not. So what we can see is the gold leaf electroscope is actually negatively charged. Red light is first shine on the surface. The gold leaf actually remains in its original place. UV light is shown on the surface. The gold leaf fall down rapidly. How can we explain such a phenomenon? You see, if we use red light and UV light, there's a difference of frequency. Right? Look at this diagram. When we shine UV light on the zinc plate, there is electron being ejected out. So more and more electrons are being ejected out, shows that the electroscope become less negative. Perhaps it is being neutralized. Therefore, the gold leaf actually fall down quickly. But how do we explain the ejection of electron? Using classical wave theory. But actually, classical wave theory has failed to explain this phenomenon. So before we go on further, we would like to find out a few things about light itself. Is light a wave or is light a photon? Okay, or particle. Now UV light seems to have greater amount of energy due to what? Due to the equation energy equals to HF. E equals to HF. Now this H is Planck's constant. Max Planck has contributed some ideas in the quantization of energy, meaning energies are in discrete amount in particles. Okay, so it has a constant of 6.63 times 10 power of negative 34. Then F is a frequency. It shows that energy depends on the frequency of the particle itself. So light actually consists of particles, and this particle is what we call photons. So each photon carries a definite amount of energy. Before we go further, we look at this spectrum of light, visible light. We know infrared is next to the red color and ultraviolet is next to violet. And we know that the frequency of violet is actually higher, the wavelength shorter. For infrared, the frequency is very low and the wavelength is very long. So because of this, we can make such conclusion that the violet light has greater amount of energy than the amount of energy in red light. If you consider a violet photon, the amount of energy it carries is actually greater than the amount of energy a red photon will carry. Energy lesser. Energy is quantized in packets or bundles of energy. So like we said just now, it is in the bundles of photon. Okay, all the energy is in a discrete amount. When we say discrete, it has something to do with a definite amount. Just like when we walk up the stairs, we can only walk step 1, step 2. We don't walk 1.7 steps. So this stream of ray of light, if you look inside, it is actually a stream of photons, stream of particles. You can think of it as rivers without the water, but a lot of colorful ping pong ball flowing along the river line. So this photon carries a definite amount of energy. So let's revisit the situation. If we have a photon, we have streams of photon coming in and striking the surface. Actually, there are many photons going to strike the surface, but the photon is actually working on one principle. One principle is one photon transfer energy to one electron, one-to-one basis. So this photon will strike this electron, and this electron will be ejected out. So we must consider this. Let's say this photon has 17 joule, and this electron actually is bound to parent atom. You see, each electron is bound to the parent atom. So there is some kind of energy involved if you need to remove the electron from its surface. And this one we call work function. It's like the electron binding energy. Work function in some books is written as W, in some books is written as phi. And this work function is actually electron binding energy. Some work need to be done to dislodge the electron, to remove the electron from the parent atom. So this is called electron binding energy. So after the electron being dislodged and ejected out of the surface, it also moves up with kinetic energy. It seems like we can bring out a formula of conservation of energy, isn't it? What do you think? Now, as we go into next slide, we should go back to the previous slide, and we establish a formula. And this formula is none other than, since the incident photon is coming with the incident energy, and the requirement to dislodge the electron is W or phi, and the energy that comes out is kinetic energy. So we can make one concluding formula. The formula is called E equals to W plus EK. We want to be more specific because each photon carries an amount of energy equivalent to HF. So HF equals to W plus EK. And this one we can say, hi friend, we eat Kit Kat. Just one of the way to remember. Hi friend, we eat Kit Kat.